Thanks, Mark. We were just saying this is a 3D show this afternoon and we're sitting in front of you guys and a beer, so we'll try and keep it as entertaining as possible and as quick as possible too, I guess. So, as Mark mentioned, my name's Doug Menzies, so I work for Inflection Resources, and we're exploring in the northern part of the Macquarie Arc of the Junior Narromine Belt for alkalic porphyries undercover. And there's the cautionary notes. I don't believe anything I tell you. There are a number of forward-looking statements. So we have the philosophy of making an opportunity out of exploration undercover. In some parts of the belt we're exploring, there's been limited exploration in the past in the basement itself, and we see that as a huge opportunity for our company. Inflection are a company that started through the brainchild of a number of Australian guys, and I'll describe some of that in a minute. But our company's based out of Canada, but all our assets and all our exploration is here in Australia. So yeah, we're exploring the northern part of the Junior Narromine Belt, and on this image here, that's the actual boundary of the Mesozoic Great Artesian Basin that Steve Oxenberg mentioned earlier. That white line there is the same boundary sitting on the aeromagnetic data, and you can see here, the projects Cowal, North Parkes, Tom Engley, and the extent of the mag signature north of, say, the Mile project here that Steve was talking about, north of Trangie, which sits in here. Up north, as far north as our tenement package goes as far north as Walgett, just in about here. There's 750,000 hectares of tenements in that package, and it's really interesting to us that there's only ever been 2 drill holes into the basement, one there and one by Newcrest in here. Another one that was failed in about 10 metres from the basement by Resolute back about 10 years ago. But yeah, so not really much exploration at all in the basement rocks, and we see that as an opportunity. Our initial targets, and I'll show you some more detail on this in a minute, were generated by Douglas Haynes, who was involved in the discovery team of Olympic Dam, Ernest Henry, Nifty in the west, and the Kamoa copper project in the DRC. I don't think there's a guy on the planet that's discovered more copper than that guy, and he's a lovely man. I feel pretty fortunate to be able to work with him on these targets. He's 82 and has an amazing intellect. But yeah, anyway, so he's, I shouldn't be too gushy, but he's generated a lot of these projects for us, these targets, and he came up with the original concept of chasing the Ordovician belt undercover. And we've got a great partnership with Anglo Gold Ashanti to deliver on this program. Here's our exploration model, and this is based on work by Alan Wilson in the early 2000s. But I want to labour a couple of little points here. I'm sure a number of people in the room are familiar with this alkalic porphyry model and the alteration zonation. But I want to sort of make sure that we remember a couple of points as we go. Firstly, the alteration zonation from sodic 1, which is albite, chlorite and pyrite, to sodic 2, which is albite, K-spar, illite, pyrite and tourmaline, and just remember the tourmaline, propylitic, chloride, epidite, albite, and then the central potassic core where typically you'd get K-feldspar alteration, the introduction of magnetite, and around multi-phase intrusion stocks. All right, so we're really interested in this part here to vector into to the central core, and we're also interested in that magnetite enrichment, which will give us a vector based on the geophysical data. Now that could be a zone of magnetite high in the aeromagnetic data, or it could be a zone of magnetite depletion or a mag low based on the alteration above it. So we've got to consider both those things. And of course these things, as we see at Parkes, for example, are very, in the case of Parkes, can be quite narrow and very vertically extensive. Oh, let's go back a slide. So to give you a feel for the sort of signature, and Steve showed a bit of this slide earlier, Douglas Haynes, in the original work and generating these targets for us, used a number of these projects as case studies. So Cowal, Parkes, Cadia, Boda, and he looked at the geophysical signature of each of those projects, both in the aeromagnetic data and the gravity data, and used that as training data sets for our ground further to the north, up here north of Parkes, up in through up to Walgett. Now it's important to note here, and I'll show you in a bit more detail, and Steve mentioned this earlier, Steve Oxenberg, Parkes has got a very pronounced, and it's been known about for decades, the gravity low associated with the Parkes ore body, and that's really thought to be the manifestation of the batholith, the depth in that project, which is driving a lot of the porphyry stocks coming off it. Likewise at Mile, another really interesting mag low that Steve was talking about. Now, we are quite interested and excited by the mag low and the embayment, gravity low and the embayment in the gravity that we're seeing here in the Duck Creek project area. I should say from the outset, that's gravity on this side and this is aeromag on this side. Now, likewise, if you look at the signature for Parkes and Cowell and Boda and Cadia, they are manifest as mag highs. On a broad level, I can't show you the more detailed data over Parkes, but there are, on a minor level, each of the deposits around Parkes are manifest both as some cases mag highs and in other cases as circular mag highs with a central mag low. So you've got to bear both those in mind. So now zooming into our tenement package, that's Trangie just there, Warren here, and then heading further north, and Nyngan sits in there, the township of Nyngan, with the Big Bogan. And so this is aeromagnetic data. It's total intensity reduced to pole aeromagnetic data on the left-hand side and Booga gravity data on the right-hand side. Now that's the pronounced gravity low that I was talking about in our Duck Creek tenement, which we've done quite a bit of work on. There's this pronounced aeromagnetic high in that area, which we call the Duck Creek aeromagnetic complex, and we've done quite a bit of work on that. Now, as I mentioned before, Douglas used all these known porphyry deposits as training data sets, in other words, Parkes, Cadia, Boda, and Cal, as training data sets, and developed a number of different targets throughout this whole belt for us, all of which we're in the process and have been testing over the last 15 months under the agreement with Anglo Gold Ashanti. These other tenements on the outside are not part of the JV. So now just zooming in down into the micro level, I'm going to start with, actually let me just go back a sec. I'm going to talk in detail about our Mile Mundy project and our Duck Creek projects, both of which we're quite excited by some of the results we're seeing. Again, this is early stage exploration. I'm not going to show you intercepts of huge amounts of copper because we don't have that yet. We are paid to be optimists and we feel that we'll get there, but we're really looking at early stage exploration, and it's exploration undercover. It's exciting stuff that really hasn't been done before in this part of New South Wales. So zooming in on the Mile Mundy project. So this is again aeromagnetic data reduced to pole aeromagnetic data, and so we've got a bunch of drill holes that we've drilled in this Mile Mundy project area. There's a large zone of elevated aeromagnetic data, mag highs, and a small zone of depleted mag signature there, and I'll talk about that in a bit in a minute. From the the top of hole analysis of all these drill holes through about 180 metres of cover in this particular area, and as Steve mentioned, the cover is generally unlithified sand, silts and conglomerates. We've drilled over 100 holes throughout the Mesozoic belt, so if there's any student that wants to do an honours thesis on the Mesozoic cover, come and see me, but I wouldn't recommend it, but there's plenty of data. And in the central portion of this aeromag feature, we've intersected a couple of intrusions, so we've got a diorite, a quartz monzonite, and there's a granite in there as well. And the larger areas is feldspar-ferric andesites and volcanoclastics, intercalated sequence. it seems to be inclined, but with the limited amount of drill core data that we have there, we need to get a better handle on the orientation of the stratigraphy. Now, just to point out some alteration before we move on to the next slide. Dominantly, these andesites and volcanoclastics exhibit chloride epidote alteration with quite a bit of albite in some cases, and the intrusions are quartz case bar, biotite albite altered, in this case biotite albite alteration with the latest sericite carbonate overprint. So just talking a bit more about alteration at the Mile Mundy project. I mentioned that zone of subdued aeromagnetic signature. This drill hole here, which after some analysis by Alan Wilson, we got Alan to come out and look at all our drill core, and this is one of the earlier drill holes that we drilled. He really liked that alteration, and there's quartz carbonate, chalcopyrite bearing veins. So that led us to follow some of that, follow that early hole up, which is hole 3 into Mile Mundy with some additional holes. We then intersected some quartz chalcopyrite veins in epidote altered andesites. Similarly here, quartz chalcopyrite bearing veins, and additionally some quartz chalcopyrite moly bearing veins. And typically in a porphyry environment, molybdenite doesn't really travel very far away from the central magmatic source. Now moving north to Duck Creek, now just to put you back in the geographic sense, so we've just talked about the Mile Mundy project down here just north of Trangie, and then this is the Duck Creek EL in here. Now we've drilled a few holes in the central portion of Duck Creek, but most of our focus has been on this northern, what we call the Duck Creek aeromagnetic complex. These images here are reduced to pole aeromagnetic images with a first vertical derivative filter on it, and you can see there's a number of curvy linear shapes in it. Now it was interesting, we first identified these lows, which we called the eyes in the aeromagnetic data, and the first hole we tried to drill into this low, central low here, failed, but the second hole got into the basement and shows some pretty encouraging alteration for us, and I'll show you the next couple of slides of that. Now all these holes that I'm showing here were drilled prior to a ambient noise tomology survey, which I'll show you in a moment as well in the next couple of slides. But we all talk about technical success, right? So in this case, our technical success was actually getting to the basement because there's a fair amount of cover in this part of the world. So we're actually getting to the basement in that hole too was a success for us, but even more, we intersected some pretty encouraging looking rocks. So for example, and this is hole 2 here, we're talking about hole 2, hole 5 and hole 16. So if you cast your mind back to the slide of our exploration model, Steve Oxenberg mentioned it, Pete Dwerden mentioned the importance of the sodic alteration or the interest in, I suppose, in sodic alteration at the Cadia district, where we've got albite, case bar and tourmaline. And so in these holes, the first thing we picked up was a lot of tourmaline. That's those black dots there. Tourmaline alteration with albite and hematite. And likewise, these are actually volcanoclastic conglomerates. Likewise here, albite tourmaline in a volcanoclastic conglomerate. These are both in the first hole. Likewise, this one here, where we're seeing similar albite with hematite alteration and veins similar to the style defined as B-style veins, so quartz pyrite veins, not much chalcopyrite, but dominantly pyrite dominated. Now, I've taken the liberty of putting some photos in from Cadia East and Cadia Ridgeway. This photo here is from Alan Wilson's PhD, albite alteration with tourmaline. So you can see there's a fair comparison between those two. And likewise here, Cadia Ridgeway core, where we've got these sort of B or B-style veins, I suppose, in a hematite altered andesitic rock. So similar to what we're seeing here. Also interesting in a step-out hole, hole 16, which sits out in this part of the world, where we intersected almost entirely a hole of almost entirely monzonite, different phases of monzonites. There were quartz monzonites, feldspar-ferric monzonites, a number of different intrusions which exhibit these quartz chalcopyrite pyrite-bearing veins, typical of a B-style vein under the Gustafson classification. And then, interestingly, in hole 5 as well, we intersected these sort of enigmatic clots of bornite, magnetite and epidote rings. And we see quite a few of these, and it gives us an indication that we're seeing a level of fertility in the system. Oop. Just some more examples of alteration. Likewise, hematite, strongly hematite-altered volcanoclastic. Similar epidote pyrite clot. Again, pyrite tourmaline vein in a biotite, hematite-altered volcanoclastic conglomerate. And then we also see, which is encouraging for us, is these massive quartz magnetite-bearing veins that, again, should give us a level of proximity to the magmatic source that's deriving this alteration within the hydrothermal system. Just talking a little bit about lithogeochem. As we go from the southern, we looked at all the lithogeochem from Mile-Mundy up through, looking at Mile-Mundy project, and then the southern part of Duck Creek, and then the northern part of Duck Creek in that aeromagnetic complex that I was just talking about, and plotted against this hasty diagram. And remember, this is very much in response to a recent paper that the New South Wales Geological Survey put out, which was really interesting in my view, talking about the use of this diagram, thorium versus cobalt discrimination, and trying to classify the rocks in relation to calc-alkaline versus high-K shoshonitic. And what we're finding is that there's a progression from more calc-alkaline in the southern area, so around Mile-Mundy, getting through sort of higher calc-alkaline up to high-K shoshonitic as we get right up into the Duck Creek proper area, the northern part. And that's sort of Tony Crawford's work, and Tony does all our petrology work at the moment, and he identified some apatite microphenocrysts suggestive of high-K calc-alkaline, dominantly in the northern Duck Creek area. What is that telling us? We're not sure. It may be telling us that there's a progression in the chemistry of the arc as we go further north, but there's obviously a lot more work that we need to do. Ambient noise tomology. I've got to tell this story. Prior to, this is back 2 or 3 years ago, when I first started with Inflection, Alistair Waddell, my boss, said, why don't we try passive seismic? And I thought to myself, what would you use passive seismic to explore for porphyries for? I'd really never seen any passive seismic work done. Now, it wasn't until we formed the partnership with Anglo Gold Ashanti, and some of their geophysicists mentioned this ambient noise tomology, which is a similar version of passive seismic, that it really sparked the interest and got me over the line thinking about it. Now, we've formed a really good partnership through Anglo Gold with Fleet Space. Now, we initially, we had a couple of different iterations of surveys. The first survey that we completed was over this northern Duck Creek aeromagnetic complex, which is basically that white box there. This image here is seismic velocity, metres per second, with the high areas being elevated seismic velocity and the low areas being lower seismic velocity. The first survey had 2 components to it. So we put out an array of 64 geodes at 800 metres apart, and then and the way it works is the geodes sit in the ground for about 4 or 5 days. They're connected to satellites. That data is automatically sent to a satellite and a supercomputer over in Adelaide. And so we're seeing real time the gathering of the data, whether the geodes are collecting data well enough. If there's any problems with the data being collected, we can go out and fix it straight away. We're also getting a good feel for the signal to noise ratio, and this is the bounds of my geophysical knowledge, right? how the signal to noise ratio is going in the collection of that data. So it's real-time acquisition, and we get a good feel for whether it's working or not. We then moved and took a more detailed survey of 400 by 400 metres in the central portion. That data, those two data sets were then merged, thank you, into this data set here. Now we think we can see some pretty good breaks in the seismic velocity data. Several of these holes were drilled prior, as I mentioned before, but what we do know is the areas that we're seeing the most alterations seem to be coincident with velocity lows. And since the collection of this data, we drilled hole 20 from west to east through that velocity high, and we intersected Monzonites. We did a downhole wireline seismic velocity survey, and we are reasonably confident that where we're getting high zones of sonic velocity downhole from the wireline data, coincident with the Monzonites, but also coincident where we're seeing high velocity areas in the ANT survey. There's a difference in the magnitude of both those surveys. One's gathered at 1 centimetre readings, and the other one is gathered at say a 20 metre square, but the data sets seem to be fairly comparable. So that is supporting, in our view, the hypothesis that, and I think Steve might have mentioned, or no, sorry, Pete might have mentioned this earlier, that zones of high velocity are representative of potential intrusions, and zones of lower velocity could be representative of structures or zones of hydrothermal alteration. And the other thing that is supportive of that hypothesis is this hole 16, which I showed you back here. This monzonite sits in that zone of elevated velocity. We then worked again with Fleet, and they completed a much larger survey over using 100 geodes at 5.5 kilometre centres, running, thanks Mark, running from Duck Creek right down to Trangie. Now again, we picked up a number of zones. This is again velocity metres per second at minus 400 RL. And we picked up a number of zones of elevated velocity, plus some breaks in the data suggestive of structures. And we think that these large, high velocity zones are possibly batholiths at depth. So, in summary, the current drilling at Duck Creek project has defined a large zone of greater than 2 kilometres of porphyry-style alteration, classified as interpropylitic to outer potassic, characterised by albite, tourmaline, hematite, case bar alteration with indicators of fertility defined by minor copper sulfides, porphyry-style quartz pyrite plus or minus chalco veins with some these minor magnetite clots, which are really enigmatic sort of manifestations. And then the drilling at Mile Mundy intersected biotite case bar altered intrusions, quartz chalco plus or minus molybdenite-bearing veins in sericite epidote chloride altered andesite. Lithogeochem is suggesting there may be a transition from calc-alkaline in the southern portion of the tenement to more high-K schistonitic in the northern part of the Duck Creek area. The ANT data that we've developed so far suggests that elevated zones of seismic velocity are coincident with where we're seeing monzonites, and so that hypothesis seems to be standing up, that high velocity intrusions are represented as high velocity, and lower velocity is potentially alteration. The additional ANT survey lows may be suggestive of batholiths at depth, and we're looking at a strategy whether we're going to follow those up or not, but we probably will. That's it for me.